know if flies like wine and coffee or something. Porque en el vino también está.
Sí. Hello, everyone. Another day, another lecture. Do a little recap. Well, first of all, maybe I should mention here. Let me put it up there. We got a conference, right, in Argentina, 10th of November. Get your articles ready if you're going to participate, okay? And put them up there at the Rational Scientific Method, or you can put them here on Patreon, or there's also a site in Facebook for the conference itself, the 6th conference. Okay, just a heads up, a reminder then. And let me do a little recap of what we did yesterday. And let's go with this. We did time dilation. Einstein essentially was the guy who restarted this. You can say he reinvented time. That's, I think, a good way of putting it. You know, everybody just thought time was just time, like what you measure with a clock. And Einstein said, well, it's a little more complicated than that. And so he said, well, there's a relationship between time, the speed of light, and space. These three things are related, according to Einstein, okay? And so he says they're related, and if light travels at a constant speed, it's always a fixed velocity. What has to give in an equation, if there's any variability, it's got to be because of time and space. Those are the ones who have to give. And he came up with a thought experiment, and it goes something like this. Here you have an individual, we'll call him an observer. He's standing on a platform. And remember, this is 1905, 1907, thereabouts. He says there's an individual on a platform, and the train goes by. Just at the moment that the train goes by, two lightning bolts hit. One hits the front of the train, the other one hits the back of the train. And the observer is standing exactly in the middle of the train, with respect to these 2 points. He's equidistant from them. He's got the same distance with the points where the lightning strikes. And so he's got the same distance, and the light from those two events, which happen simultaneously, right, reach his eyes at the same time. No problem there. We can all understand that. What is the problem? The problem, he says, the passenger on the airplane, he sees something different. He hits the front of the train, the lightning bolt that hits the front of the train hit before the one in the rear. And why is that? Because he's moving in the direction of where the lightning bolt hits the front. So his distance decreases in that direction. By the time he receives the light from that event, it has less distance to travel to his eyes than the one he's getting away from, which is the rear of the train. Okay, and this is the issue. The issue is that Einstein says they're both right. They're both right because what the observer on the platform sees is what he sees, what he experiences, and what the guy on the inside the train sees is something different, and he's correct too, because that's his experience. And I'm saying, well, we got a problem. We got a problem because he's relying on observers. He's relying on testimony. He's relying on what each one of these guys experiences. That's where we have our first problem. And again, it's the analogy we used with Muons yesterday, and that's that, the guy in the car who throws the ball up and down. For him, the ball went up and down straight. That's his experience. But an observer on the street, sees the car go by, and if he were to look at the trajectory of the ball, it would describe a curve. So who's right? Well, the observer obviously is right. The impartial observer on the street, because he sees that curve. The guy inside the car does not see the curve. For him, the ball went just up and down. And it's the same situation here.
Well, to clarify that part, neither of them are right, because you have to take account the spin of the Earth and the spin of the...
Correct. So there are more variables, but assuming the guy in the street is more correct than the guy inside the car if we're going to use his frame of reference.
He's closer to the actual movement
Correct.
of the ball.
Right. We certainly cannot take the testimony of the guy inside the car and take it into a court of law and say, look, this is what happened. No, you can't, because he is dead wrong. And what Einstein says, these guys are all correct. And this is wrong only because Einstein is relying on testimony, on observers. And that's essentially what mathematical physics relies on. Okay, so how do we solve this problem? Well, we solve this problem very easily. What I do is put Einstein in an electric chair, and we can do this with a light detector. We don't need to fry anybody. We can just attach 2 electrodes or whatever on the tracks, and the only way that we can detect the light at a certain point where the electric chair is if the wheels of the train touch those 2 electrodes exactly at the same time. There's only one point at which the 2 wheels can touch those 2 electrodes, and the distance to the electric chair in this case, right, to that distance is the same for both. So if we have a little lamp there and we somehow send a signal, a light signal, and the lamp turns on, it can only turn on if the wheels of the train touch those 2 electrodes exactly at the same time. So now we have a notion of simultaneity. And so it doesn't matter what anybody says, whether the guy on the electric chair or the guy on the train says, well, I saw this and I experienced that. That doesn't matter. Here, the light turns on only if the signal comes from both electrodes on the tracks, okay? And so, here we have an objective criteria. We don't need to use any equations. We don't need to seek any testimony. We can do this simply with an experiment. And this is something we can do here on Earth. Okay, that's one of the issues we touched yesterday. The other one is another thought experiment. And it goes something like this. We have a passenger, the little P at the bottom, and he shines his flashlight against a mirror that's inside a moving boxcar. Again, we have the boxcar moving from left to right, and the passenger is simply shining his light at a mirror, and the light goes to the mirror, allegedly, and the mirror reflects it back to him. Okay, so we have 2 times distance. Light travels back and forth. Okay, what is the problem? The problem is that according to mathematical physics, light consists of photons, of discrete particles. And the first question is, does light function like a water sprinkler? If that's the case. For example, here I have the situation of the sun. Every atom in the sun constantly emits photons, one right after another, but the sun is spinning. So if the sun is spinning, all those little balls that each one of the atoms is emitting should travel like a water sprinkler, should just scan all around the sun as the sun spins. And if we apply this mechanism to the boxcar, what do we get? Well, we get here this strange situation where if the boxcar is 1.5 million kilometers long, since we're doing thought experiments, I guess that's acceptable. You would have to point the flashlight to where the mirror is going to be in 5 seconds, because light is going to take 5 seconds to reach there. And if you point it straight at the mirror, the mirror's not going to be there when light gets there. So you have to point it to where you see the dotted mirror in between the 2 boxcars, and you would have to point it to where the mirror is going to be in 5 seconds. But then this also would suggest that if a train emits light, you would have to add the velocity of the train to the velocity of light, and that is clearly not the case, and that's exactly what special relativity says, that you do not add these 2 distances. But then the question is, do you have to do something with these distances when you're moving sideways, when you're moving horizontally with respect to the flow of particles that are moving towards the mirror? And again, it's up to special relativity to answer this question, not for us. They have to give us an explanation of how it is that if light consists of particles, that you do not have to point the flashlight to where light is going to be in 5 seconds. That's the question relativity has to answer.
Well, I think the thing that makes light so special in that context is always the fact that you don't add the speed of light to the speed of the train. See, I think we did it right with yesterday when we were talking about a baseball. In a normal situation, if you just have a baseball and you throw it against the wall to catch it, you don't have to throw it at an angle because the ball has the momentum that you have that the train has. So you kind of don't have to consider the speed of the train.
Right, but then
with light, since you don't add the speed of the train, so the train has the movement, you have the movement, the mirror has the movement, but light doesn't care about the movement of the train because it always goes the same speed. So there, it would be strange if you threw, photons, a baseball, and you're not throwing where it's gonna go. You throw it exactly as you would
where it's gonna be, where the target's gonna be in a few seconds.
Tricky. It should be different, is the point.
Yeah.
It since you're not adding the speed of the train. How do we say the other day? If the train is moving, regardless of how fast the train is moving, light would always go and come back at the same speed if it were a photon.
Yeah.
But then, how do you reconcile that with the speed of the train? If the train is going, extremely fast, how do you throw that ball that doesn't care about the speed of the train?
Yeah, and I think what this does is it debunks the possibility that light could be mediated by particles. That's what this does. That's one thing. The other one is that, if you're going to model it with particles, it's up to the relativist to tell you what the mechanism is for light to avoid having to go in curves. Because then you have, here they use the opposite argument when they talk about light coming from a distant star during a solar eclipse. Is that a lunar eclipse, solar eclipse? The sun is blotted out, right, by the moon. The moon is between the sun and the earth, and we have this light going around, supposedly around the gravity well. So now light is curving. All the little photons, they're kind of adjusting themselves to this curved wall that they meet. So now light is curving, and it no longer travels straight. And so if light can curve, you would think that because they're all made out of little particles, all these particles are kind of rolling along this warped canvas or light gravity well. Well, then we can use the same argument in the boxcar experiment. If light is going to curve, or if I can make light curve, not in this case because space is curved, but because I need to focus where the mirror is going to be in 5 seconds, then I have to point the flashlight to where the mirror is going to be in 5 seconds. And if not, it's up to the relativist to tell you what the mechanism is to avoid that. Why don't I have to point it, to where the mirror is going to be in 5 seconds? So that's the question falls in their court. The ball is in their court. That's all I'm saying here. Okay, so Einstein comes up with a little equation that looks like that. It's not so monstrous as it looks. All we're saying here is that time of the observer, the little o, time sub o, is equal to time of the passenger, time sub p, divided by that square root of 1 minus velocity of the object over velocity of light. What is Einstein saying? He's saying that if the velocity of the object approaches that of the velocity of light, that number approaches 1. And if you get it to a very high number like 0.99, which is almost 1, which is way at the bottom, 1 minus 0.99, then you have a very small number, square root of a very small number, which makes the time of the observer, the time sub o, be very, very, very large. Okay, this is the problem. Why is it a problem? Because, my son comes up with a very good argument, which I love, absolutely love. Now, I told him that he gets a pat in the back for coming up with the argument. But see, I should get the Nobel because I came up with the equation. So, I should get the credit for coming up with the equation. So what did I do? I replaced the velocity of light with the velocity of sound. We're going to put a blind man on the train, a passenger, and we're going to put another blind man as the observer.
So we have to be blind. They can have their eyes closed.
No. I'm going to have them blind. I want to make sure these guys can't see anything. So we can't use light because none of these two guys can see. We're going to use their ears. We're going to use the speed of sound. And the speed of sound in the little green box there in air is 343 meters per second. You have different velocities in water and steel. But we're going to use the one in air, which is what most of us use, or that's our experience. So we have one passenger and we have one observer. The observer is on the platform in the station, and the passenger is on the train. And so now let's do the same equation that Einstein proposes. And there's two issues here. The first one is whether we can do a substitution and substitute light with sound. And I don't see why not. I mean, why use light as a standard? Because it's the speed limit of the universe? Who cares? What does that have to do with perception? Einstein says, what the guy sees, he's going to see the lightning bolt, the light from the lightning bolt at such time. Well, I can use the speed of sound as well and say, look.
To clarify, what he really says is that time goes slower if you're going faster because
you approach the speed of light.
Well, because the signal takes longer to get to you.
But we're only talking signal of light.
But then essentially he's equating the duration signals get to you with time.
And again, we're talking about light. How it gets to your eye.
Even sound. What he's equating is time is to him is literally the time it takes is the amount of time or the ratio of time, the passing of time, whatever you want to say, is equal to the length that the amount of time that it takes for the signal to reach you, whether it's light or sound.
Right. And so I can replace with sound.
He's saying if it takes longer for this guy to notice than this guy, then time is going slower for that guy.
Correct.
The first guy.
Correct.
If guy A notices whatever he needs to notice in 30 minutes and guy B notices it in an hour, then time
is going slower for that guy.
For him is saying, for Einstein, is time is going slower for Mr. B.
And that's correct. And that's why I'm saying that as far as I'm concerned, I see no reason why I can't replace light with sound in this experiment and in this equation.
We're just talking about detection.
Yeah, we're just talking about when the guy, the passenger, and when the passenger and when the observer on the platform, when they receive a signal, and in this case, it's a sound signal.
The way I equated it to my dad yesterday is in school we had these hearing tests where you had to raise your hand as soon as you heard the beep.
The sound.
Yeah.
You got the
big headphones, and as soon as you hear like a very soft beep,
you're supposed to raise your hand or touch the button
as soon as you notice it. But as soon as you notice it, that doesn't mean time is going slower because it took you longer to notice it.
Right. It's kind of like the Galileo opening the lantern.
You love that one, don't you?
Yeah, I love that one. The guy in the other mountain, he has to open it as soon as he sees your light. The little candle inside here.
We're on a 20-minute recap here, bro.
Okay, anyways, the point is if we replace light with sound, and I don't see why we can't do that because, again, as Hans just explained, we're just looking at signals. And here we're talking about a sound signal. Well, then we get into very weird situations because let's just do it again with 0.99, the bottom value, right? 0.99 percent or value of the speed of sound in air. So we have 1 minus that number, which is a very small number. It's 0.01. And if we divide the time that the passenger experiences divided by that, the time of the observer, the time sub O, is going to be a humongous number.
An easier way of putting that is if we're going at the speed of sound, then time stops for the observer.
Yeah. Completely, and that's
but
because
that doesn't make any sense.
Yeah, he never heard it.
Sound,
He never heard it.
Just because he never heard it doesn't mean we stop time.
But again, what we're saying here, if we use that equation with sound, then the time that the observer the time it takes the sound of the lightning bolts to reach the observer is almost infinite. It takes 1,000,000 years for him to listen to the sound coming from an event that just happened, a split second ago. And that's what shows you that relying on observers or turning this equation into something that's got to do with physics converts it into something completely absurd. You can't accept this and say, oh, this is the equation of reality. Okay? So, that's our criticism of that. And then we have something else here, and that's that Einstein, let me put ourselves back here. We have another issue, and that's that as a result of special relativity, Einstein has another absurd conclusion, totally irrational. And that's that you have a twin brother, and he travels to the stars at almost the speed of light. It's always slightly less than the speed of light. He can't travel at the speed of light because it becomes absurd. He becomes energy.
And that's when it gets weird.
Yeah, then it gets weird according to the mathematician. Fortunately, they figure that one out. But if he travels at 0.99% of the speed of light or 0.95, then we really have absurdities. Because what happens? This guy takes an atomic clock, a perfectly atomic, functioning atomic clock, which they synchronize before this guy leaves. Okay, so he goes out there, he travels near the speed of light, goes around the black hole, and comes back. Right. So he comes back, and he reaches the Earth, and he finds that his brother is an old man, could be his grandfather, and he's only aged 1 year or whatever. And that's the absurdity that Einstein reaches. And it's not just the clocks showing this difference in time, but biologically. They say, because otherwise, who would care? We say, well, yeah, the clocks had a problem, right? But no, he says biologically, physiologically, these guys are totally different. This guy has aged and this guy has not.
Could you, by that same logic, say that you could assuming you could make a fridge that spun things at the speed of light, could it hold things in perfect refrigeration? Essentially, you put an apple in this thing that spins it at the speed of light, so that it's always going.
Yeah.
So the time
spinning
stops.
of the.
So you stop time for the apple until you need it. You open the fridge, and then you got the fridge. You open the fridge 30 years later, and since the apple was moving at the speed of light, we don't care which direction.
Then it's just like fresh as the first day, right? Yeah, I guess you could come up with 1,000,000 scenarios.
It gets weird.
Yeah, it's more than weird. It's just totally irrational. And that's the criticism against it. And what is the solution to that?
Wait, real quick. Where does gravity play in the twin paradox? Does it have any?
No. Gravity doesn't really count here because this is a special relativistic effect, and special relativity is gravity-less.
Oh, that's cheating.
Yeah, it is. It's a situation where we don't use gravity. Okay, so we're not using gravitational time dilation. It's all kinetic time dilation. That's important. It's time dilation related or based on motion. Okay. This guy comes back, and his clock measures different simply because this of the kinetic time dilation. The fact that motion affects, according to Einstein, affects time. Not the speed of light, because that's always fixed, okay? But what's the issue? The issue is, or how do we debunk this? Well, it's kind of easy here. Where is it? Here.
With common sense.
What? Common sense debunks
common
it.
Sense, yeah.
Here's what Einstein predicts. And again, this is not an explanation for anything, by the way. That's why it also has nothing to do with physics or with science. They're not explaining anything. All they're saying is this is what we predict, or this is what we observe. They're not explaining anything in the sense that they're not explaining the physical mechanism. They just say, look, this is what our equations predict, that this is what should be. But at no point have they given and they can even do something in the lab and say, see here, we've again proven time dilation. What they're doing is only observing and reporting on what they observe. They have not explained the mechanism. What is the mechanism that makes one individual age more than the other? That's what they have to explain, and that's what they don't explain. So what's the situation? The situation is that In the case of Einstein here, he's counting whatchamacallit, he's counting seconds. He's going to tell the age of these people using seconds. He's going to add up seconds. And he says that the seconds of the guy who's traveling, are dilated. They come farther and farther apart. So the guy is not aging. Whereas, the guy on Earth, his seconds are normal, so he is aging in comparison at least to his brother. And the problem here is, again, what I say is, in the case of time dilation, this is a very easy thing to answer. We don't use seconds to count how old you are. We don't put the number of seconds, one candle for each second in your life on a birthday cake. What we do is we put one candle for each year on the birthday cake. And the year is still defined to this day in the same way it was, 100 years ago and 1,000 years ago, which is one revolution of the Earth around the sun, which is what you see on the right-hand side. That's the year. One revolution. We don't even need a number for that. We just say, look, one revolution, we'll call that a year. And so, how many times did the Earth go around the sun, irrespective of the motion of the twin that traveled, and irrespective of whether the first twin is in a inertial frame of reference? Who the hell cares? The number of times the Earth went around the sun is 20, for example, right? When the other guy comes back, he says, how many times did the Earth go around the sun? It went 20. That's the number we have on our birthday cakes. You can't say, well, I'm 50 years older than you, Johnny, because, I traveled out and my clock measured seconds differently than yours. You can't do that. Not in physics. In mathematics, you can.
Well, there's two things with that. One is what you're saying, where the way we measure time is
with a clock
is independent. No, it's not even with the clock. It's with the sun, with the Earth going around the sun.
Yeah.
Especially when we're talking about years or age.
Put this down here.
But there's two different types of age. There's like birth age, like how many times has the Earth gone around the sun since your heart started pumping? We call that, how old are you? But
yeah,
that's different than biological age, which is what they also bring into this.
Yeah.
Assuming the Earth only went around the sun 20 times, they're both 20 years older.
Yeah.
Normally speaking. But does the other guy does one guy look 20 years older and the other guy actually didn't physically age 20 years?
Yeah, and
biological.
This is the issue here is that these people are extrapolating equations and reaching irrational conclusions in physics. And the question is whether that's legal. Yeah, we are allowed to do that.
I'm interested in the biological. Like, okay, they're both 20 years older, but is one biologically different? Did one guy's cells split slower? I don't even know how you would...
Yeah. In other words, is the splitting of cells, which is one way that we can measure, age. Another one is
biological age.
There's an even better one. I like this one better because this one I think is more objective. We take a tree. The guy who travels with a tree, and we have these two trees. They were born at the same time. They have the same number of rings. Okay, so they have 3 rings when they start out. Okay, so this guy travels now out there.
Comes back
now we're going to talk about biology, right?
He comes back 100 years.
How many rings are on the tree?
The Earth has gone around the sun 100 times. So he comes back after 100 actual years. What do both trees look like?
Well, see, this guy used artificial light to continue giving
assuming
photo.
they both, assuming they both had the same amount of light, same water.
This guy's using a different kind of photosynthesis. He's using artificial photosynthesis.
Okay, but assuming both plants live the exact same life.
No, but you have to do, because obviously a tree grows only with photosynthesis. No problem. We have all these lamps aboard the ship, and we can have them bombard the tree with the same amount of photosynthesis that he would receive on Earth. Now this guy travels at the speed of light, whatever he wants to travel. Now he comes back. Now let's look at the trees. How many rings do those 2 trees have? Is there a difference?
To put it clearly, both trees were born the same. They're siblings. They're twins. They're clones. They live the exact same life in those 100 Earth revolutions around the sun.
Yeah.
When they come back, this guy's been moving at the speed of light.
That guy's dead. He's over 100 years
Yeah,
old.
no, because time dilated for him, so he's fine. But what about the tree? That's the one I'm interested in.
Yeah, the tree should have how many rings?
Does one tree have more rings? The one on Earth, does it have more rings than the one?
Right, and I'm saying
that hard to believe.
And I'm saying you can't extrapolate that.
I mean, just common sense. You think, okay, if I'm on a train that's going really fast, what does that have to do with how old I am?
That means that a person who travels every day, because any speed really is relevant for the equation. Yeah. It's just that when you travel at normal speeds, you don't age as much, But this means that the person who travels more, or if you traveled more, you're going to age less than your brother who stayed at home all day long.
Okay, but hold on. There's a big thing that
couch potato.
What if you're on the moon? Do you age faster because the moon is going slower than the Earth?
It's the same situation. All these, in other words, you're saying
but
the motion
because you just have to be going at the speed of light or close to it to get this weird effect, right?
Yeah.
But we don't know if we're going.
But any speed, they say that any speed already affects you.
Yeah, but to make it more absurd, if we take into account the motion of the Earth spinning around the sun, and God knows what motion in respect to all the matter in the universe.
Yeah.
We can't really say how fast we're really going.
Yeah.
I'm not standing still right now.
No, and the entire solar system, let alone the galaxy, is moving around other galaxies. At what speed? Are we moving close to the speed of light? Should we factor that as well? Because we're moving with respect to other galaxies. Our star moves with respect to other stars. And we're moving with respect to the sun. So, I mean, it gets monstrous after a while because you got to kind of find out how the speed of one guy affects the other guy. Mm-hmm. Not to mention gravity, if we introduce gravity and say, well, Jupiter now came around and is close to the Earth. Now there's gravitational influence, whereas when Jupiter's on the other side of the sun, that time of the year, that doesn't affect us as much. If you factor that, it's a total monster.
I think if time dilation, according to motion, were true, that means train drivers would look very young because they're always on the move. Or truck drivers.
Or they should try to drive at the speed of light.
No, I mean anyone who moves as a profession, like a truck driver, they all look younger than they are because they're always.
And they're always fat. I don't know why.
If anything, they look older than they are. I don't know. Something's off with that. Motion equals slower time.
And then we arrive on another more absurd, and I think this one is.
You can't get weirder.
Oh yeah, this one's I think the weirdest of all. Forget about the twin being older than you, that kind of thing, or younger than you. Here we have something which is even worse. It's the muon. Okay.
What's a muon?
Muon is a little particle that they have invented. Okay, so the muon, what is it? Muon is a particle that, specifically, it's like 200 times more massive than the electron, so it's a very massive particle.
It's huge.
Yeah, huge. 200 times more massive than the electron, but the important part is that the muon only has a life expectancy. It only lives 2.2 microseconds. So, and then it disintegrates. It decays. Okay? That's the muon. So let's repeat that. A muon only has a lifetime. It's like like a little ant only can live 2.2 microseconds and it dies. It's kind of like that. The muon only has a 2.2 microsecond lifetime.
What happens when the muon dies? What do you mean by
lifetime? It's not
alive, so we're not talking about lifetimes.
We hold a ceremony at the
we bury the muon. No, but what do they mean by dies?
Okay, it decays, it disappears, it disintegrates. I don't think that's important. I think this is what the part is important. This is what one guy says. He puts it into right perspective. He says, because the muon travels, right? It travels almost at the speed of light or close to the speed of light.
Real quick, what is a muon?
Just a particle. Just a name they gave this particle that has 2.2 microsecond lifetime and 200 times heavier than the electron. That's all it is.
Is that when they crash two atoms together? Is that
what they come up with these idiotic notions.
But it's one of those that supposedly come out of two atoms crashing.
Yeah, and the way they look at it, is they supposedly monitor. They say muons are created in the atmosphere. and they come down to Earth, but they're so far away, it takes a long time. It would take like 5 seconds for this guy to reach the Earth, but it only has 2.2 microsecond lifetime, so it shouldn't be detected on Earth. They do detect it on Earth, so they say, what has happened? How do we explain this? And the explanation they give is that the muon, the distance for the muon has dilated. Okay, it has shrunk. The distance, in other words, for us, we're normal, right? But the muon is traveling so fast that for it, the distance has shrunk. And that's why we detect it at surface level here on Earth. Otherwise, it would decay in the middle of space. And here's the statement that kind of puts this in perspective. It's probably one of the best statements I found for the muon. If the distance traveled by the muon is not physically shorter, the distance traveled, right? If it's not physically shorter, the muon simply does not remain in existence long enough to make the trip even at speeds greater than 0.9 c, right? 0.9, the speed of light. The distance to be traveled by the muon from the upper atmosphere to sea level is physically shorter than the same distance measured by a slower moving particle. So we have a race between the muon and you choose the particle, pion, positron, whatever you want to put up there, no problem. For the muon, that distance is shorter because it travels so fast that it should not be detected at sea level, but it is. And since it is, and it only has a 2.2 microsecond time to do that whole travel in, what has shrunk is distance.
But do they attribute that to speed, to its speed? Because it doesn't say so explicitly here.
It says that it just says
muons have this special.
Yeah,
thing.
It says a special thing that for the muon the distance shrinks, and that's the only way they can explain it.
But they're not saying it shrinks because it's going so fast. They're just saying it shrinks because it's a muon.
Well, they use special relativity equations at that point. They try to explain with special relativity, and they say, look, if we apply the equation, we can explain this very easily. What happens here is, again, the muon is traveling at 0.95 or 0.99 the speed of light, and for the muon, that distance has shrunk.
But what they're saying is even at maximum speed, at 0.9 whatever speed of light, the muon wouldn't make it.
Mm-hmm.
So, therefore, the muon has the special characteristic that shortens distances, as well as moving fast.
Yeah, it shortens
That's
distances.
And
here is the here's first the image of that statement. Here you see the muon should decay up there in the middle of space in the atmosphere where it's created, and instead it strikes the head of the relativist at sea level, right? Why? Because for some reason the muon travels fast, but it's not the speed, it's the fact that the speed affects the distance. You know, the only thing that they say, look, even if the muon traveled at the speed of light, no problem. It's allowed to do that, maybe. If you just get your magic wand and say it is so, fine. But then something's got to give. And in this case, it's not really time that's giving. What's giving is space. The distance is what shrinks. So we have time dilation. This is now distance dilation.
I see where mathematics can get messed up because they can literally take any variable in there, and account for the missing they just have to balance the equation. They don't care if they use time to do it, or either shorten or lengthen time to make it work.
They just need to make sure the numbers are right.
Shorten or lengthen distance. They don't care what variables they're playing around with. And that's how they get these weird.
And that's why I'm saying that this mathematics, this observer-based mathematics, has nothing at all to do with physics.
That has nothing to do with observers. They're just saying that muon.
Well, they're saying that the observer detects it at sea level, so in that sense, they introduce the observer. Okay. But here's the solution. Here we have two mountains. Okay, we have a mountain on the left, and we have another mountain on the right. Okay, and let me put this here. We have one mountain on the left, another mountain on the right, okay? And what's happening? We're going to send a muon. This time we're not going to send it from the upper atmosphere to the ground. Now we're going to send it horizontally, okay? I guess it doesn't matter. The muon has 2.2 microsecond lifetime, no problem. So we just send it from one mountain to the other. The distance is greater than what the muon would be able to live. If we detect it at the other side of the mountain, it means, what has shrunk is the distance. The question is, what distance has shrunk? Has the distance between the mountains shrunk, or the distance traveled by the muon shrunk? Which distance are we going to shrink?
I'm assuming the distance traveled, or else the mountains came closer.
Right, you got it. That's the point I'm trying to make here. Did the mountains come closer to each other? Hopefully everybody says no. I don't want to put that past the mathematicians, but I would think that a rational person would say, look, the distance between the mountains has not changed. Okay, so let's look at the other distance. We have the distance traveled by the muon has shrunk, right? The numbers show us that for the muon, as far as the muon is concerned, the distance for it, the distance it has to travel, has shrunk. Okay, because we detected at the other side, at the other mountain, at the mountain number B, the one in the right in this case. So let's look at this. Is that the same distance? Is the distance traveled by the muon, assuming there's no shrinkage of distance, we would say it's the same distance as the distance between the mountains. In other words, the distance traveled would be equal and exactly the same as the separation between the mountains, whatever number of meters those are. If they're 100 meters apart, then the muon is traveling 100 meters, from one mountain to the other.
Well, according to them, it would be 20 meters.
Right. That's what they're saying. For the muon, these guys are saying, well, it's just 20 meters as far as the muon is concerned.
So to make that as clear as possible, the mountains are 100 meters apart, or kilometers, whatever.
Right.
But the muon has only traveled a fifth of that.
Right.
And made it to the other side.
Right. And so the question is, it looks like we're talking about the same thing. In other words, the two distances should be exactly the same thing. How is it that for the muon, the distance between the two mountains became 20 meters when they're separated by 100 meters? Something happened there,
The only way I could imagine that happening is teleportation, which is fictional. Is basically
science fiction.
Yeah. Where the
fantasy.
Where the muon's path would look kind of like a dotted line.
Okay, but that's what I'm going to say next. If you look at the bottom there, you'll see a lot of little lines. What are those lines? Those are, I film it. I film 1 second per frame, and there are a million frames in between them, but we're just going to consider 1 second per frame. So I got so many frames, I don't know, 100, 150, whatever number of frames you got there. And I simply film, right, from one mountain to the other, right? And I'm going to look at those frames. Let's just say there's 100 frames there. Okay, now we send a muon, and we do the same thing. We film the muon. What should we see in the film? Are we going to see fewer frames?
I guess you just don't see the muon because you said 1 second per frame, and this thing only lasts 2 microseconds or whatever.
My thing is conceptual. This is God's camera, okay?
Yeah.
So he's able to film this, right, for us. And the question is, are we missing frames? Is that what we're going to say? Is that the explanation? Are we missing frames when the muon travels in the 20 meters? What for the muon is 20 meters, whereas for between the mountains there's 100 meters. Are we removing frames from God's camera?
I think that's what teleportation is essentially. It's
removing frames.
Removing the frames between 2 frames. You just kind of take out a few every now and then. Like it's probably even where you take.
Is that acceptable for physics?
Essentially, like taking out every second frame, for example.
Right. And the question is whether that's legal in physics. I mean, can you do that? Can you say I'm going to remove frames from the film for the muon, but I'm not going to remove frames for the film where I just filmed, the distance between the two mountains? Is that valid?
Well, the muon just doesn't show itself in those frames.
And so what happened? And that's what they have to explain. What happened to the muon between those frames, those missing frames? What happened there?
It's not missing frames. I think it's essentially like the muon is blinking in and out of existence, is what they're saying. It's there and there, it isn't there, it's there, it isn't there. So it's just only doing the parts.
Yeah, it's a dotted line. It's a dotted line.
Yeah, to add up to 20 meters.
Whereas the distance between the two mountains is a solid line. The one for the muon, because it's traveling, it's a dotted line, and you can remove some of those little frames. Just remove them arbitrarily.
Not remove frames, but it's just missing from those frames.
And the question is, what's the explanation of that?
it's going in and out of existence.
Yeah, but that's not what they're saying, because they say the muon goes out of existence after 2.2 microseconds, not in between.
During. Oh, okay. Then so, they're wrong.
Yeah, I know.
They don't know their own muon. See, if I made the muon, I'd make it be going in and out of existence the whole time.
Right, and this is the issue with all of this. The question is whether any of this that violates our rationale, our intuition, whether any of this has to do with physics.
Well, some people don't have a problem with things going in and out of existence.
Yeah, I know. This is the word.
Popping in and out.
And I think they're floating in the air. I don't think they have their feet on the ground. That's the problem I see.
Well, because you have movies. I mean, Jumper is the most famous movie about teleportation, where this guy gains a power to essentially teleport to wherever he's been before.
Okay.
It's a really nice movie. I mean, yeah, the movie is really nice, I thought. I like it. But, obviously, it's Hollywood. You can't really teleport. You can't literally just be here and then be somewhere else the next second.
Is Hollywood University the same thing as Harvard or Cambridge University? Is that what we're saying?
I think they are.
They're approaching each other.
They are approaching each other. In the latest the latest most popular movie, Interstellar, is about this guy, really big actor, Matthew McConaughey, and A-list director, and they actually brought a mathematical physicist
to do the math.
To do the director had to talk to the mathematical physicist, and hey, if this happened, what would happen here? He tried to get the movie as realistic as possible.
So we're not talking about science fiction. We're talking about a document. This is a documentary.
Well, it's a movie using real life.
It's a documentary.
But it's not a documentary, because a documentary explains things about real life. This is just a movie within the bounds of reality, according to a mathematician.
Right.
So you have this guy going back in time and things like that, and going into a black hole, and time dilates because he's closer to a black hole. There's gravity. It's not the motion dilation, it's the gravity dilation.
It's what physics has become.
But you have big name directors going, because they don't know
physics.
They don't know physics. So
they have to bring a consultant.
Yeah, exactly. They bring a consultant, and he's like, look, this is what happens.
Yeah.
And the guy just says, okay, let's put that in the movie. So they are getting closer and closer together.
And so the question you've got to answer with especially with special relativity, regarding time dilation, distance and length dilation, mass increase. You increase in mass when you travel at a faster speed. No kidding. Whatever mass is, obviously the pressure is greater. What that has to do with mass, I don't know, especially if you don't define mass. Are we saying that the guy increased in the number of atoms, or are we just saying that he went from 100 pounds to 200 pounds? Those two things are kind of different, because one has to do with pressure applied, and the other one has to do with constitution, whether the fat man gained another 100 pounds. And so those two things are different. And, you kind of never know, because these people just talk about kilograms and pounds. And time dilation, same thing. Did the muon, how could the distance change for the muon and not for the distance between the two mountains, the separation between two mountains? And how could one twin be 50 years older than his twin who traveled, and so on? We have all these irrational conclusions. And the question is whether we can derive such conclusions from equations. Is this legal? Is this valid to do it this way? And that's why we have all these distorted interpretations of what physics is or supposed to be. And it gets worse when they just say they proved it. Well, the fact that you measure something in the lab or observed something in the lab does not really mean that you can explain what you saw. If you can explain it, fine. But if you can't explain, just say, look, I'm just going to describe it with a mathematical formula, and this is my conclusion. Well, that's different. That's different than saying, look, I can explain the mechanism of how this came to be. And that's where we have a distance between mathematical physics and actual physics, real physics.
Back to the unrealistic part of mathematical physics, I think the reason why people accept fantastic, quote-unquote unrealistic scenarios is because, even you got this problem with the rope hypothesis, although less so, obviously, where when you get to such macro scenarios or micro scenarios, you kind of get into the realm of the fantastic by default. So they kind of sweep everything under that fantastical rug. So it's like, oh, if one crazy thing is possible, then the sky's the limit. Let's do it. It's like no holds barred.
But then you got to go with William Ockham, which is the least assumptions or the least weird explanations, and that's, I guess, the best you can do. For example, under the rope model, we have one rope crossing another model, and people say another rope, and people say, well, that's irrational. Yeah, it is. It is from our macro world point of view. It is irrational, no doubt about it. We don't experience that in our world. It has to be suggested for the micro world, the subatomic world. But this is the issue. The issue is that that's maybe one of the few assumptions you have to make under the rope model. Everything else, you can explain with a rope model. You can explain the slit experiment. You can explain polarization. You can explain why light has this undulation type of thing, why there's an electric field running perpendicular to a magnetic field, and why they both go along an axis. You can explain a lot of things with a rope model, and then only when you get to the nitty-gritty, that's when you kind of run into trouble. But and I'm not sure we can resolve all those things. All I can say is we have the least assumptions and the more explanations. Whereas in mathematical physics, if you go with particles, you have no explanation.
With mathematical physics, with particles or waves, it's like I said the other day, where you end up with more questions than answers.
Correct.
Where it literally feels like this. Like the holes in the boat, and you're plugging one hole,
and another one goes out. It's like bubble gum.
One. It's like it doesn't work.
Well, one guy is putting bubble gum, the other guy's drilling holes.
Yeah, it's like kill the guy that's drilling holes. So it feels very ad hoc, and it's like you're trying to spin plates. Like, okay, if you have a particle, then this is this, that, this. There's a problem with that. There's a problem with this. When you have so many problems stacked on top of each other, you go, hold on. Is this really how light works?
Yeah, and so that's all I can say. I can say that the only reason you should choose, and again, that's your option, but the reason I at least choose the rope model over particles is that with the particles you can't explain any phenomena. In fact, if you look at just about anything, Compton effect, the photoelectric effect, whichever one of these experiments that have been done in the lab and been proven, been observed, and et cetera, they all require waves. You have to, the explanation comes with waves. And you say, well, what does the particle have to do with, what does the discrete photon have to do with that? If the explanation is going to rely on, wavelength and frequency. And this is where they come in, they say, well, we have a duality, light is both. And that's what's irrational. And you have to make that assumption in mathematics or mathematical physics in order to give some kind of physical interpretation to this phenomena. And under the rope model, you don't have to do any of that. The only problem with a rope, again, is when you get to the nitty-gritty and say, well, how is it that one rope goes across another one?
I wanted to get into some Quora questions before we finish.
Oh, okay. Yeah, go ahead.
A few in.
Yeah.
We've been talking about time a lot, and time is, as many people know, one of the. Well, I guess I just asked the question: is time a dimension?
Yeah, and again, I'm saying
when we're
time.
talking about 4 dimensions. They talk about the 3 dimensions of
right,
space
plus one
plus
of time.
So.
And again, time is not a dimension, and the problem here is that the mathematicians use the word dimension. They have a weird definition of the word dimension. In normal parlance, in ordinary speech, we say that something is 3-dimensional. What do we mean by that? We're saying that thing, if we take any point inside any location, from there we can, in order to describe this thing, we have 3 90-degree straight lines that can come out of that point, and we can point to any other point within within that thing. For example, here I have the pot, right? And you take any point in there, you need 3 lines to locate any other point. Or you can establish the location of that point with 3 lines, or you can say this location there, right? Or this atom, or whatever unit you want to use. points in three mutually perpendicular directions. Now, if you did that at 2 o'clock, does that change if you did it at 4 o'clock? And so time has no bearing on that physicality, okay? So when we say something is three-dimensional, that's what we're referring to. The mathematicians have turned that around and say, look, a dimension is something different. The dimension is the location of that point with respect to three arbitrary, other locations. You're inside the room, you say, well, how can I locate myself? What would I say about location, my location? Well, you take one line from one wall, one line from the ceiling, and the other one from the other wall, and they're mutually perpendicular, right? Three lines are mutually perpendicular, and you can locate me at this point. But that happened at 2 o'clock. At 4 o'clock, I'm in another point in a room. And so now time becomes a dimension, another variable here that we're using to locate me within the room, and it's got to do with different times. And but what's the issue? The issue here is that they're not talking about dimensions. They're talking about number lines. They are concerned with numbers. They're saying, look, he was 5 feet away from this wall, 2 feet from the ceiling, 10 feet from the other wall, and that was at 2 o'clock in the afternoon. And at 4 o'clock, he was at someplace else with different numbers there as well. And so what are we saying? The guy is concerned about number lines. He's counting the number of tiles, or he's unrolling the measuring tape and saying, look, this is so many meters. And so he's looking at numbers. And that's those numbers, when he has his XY coordinates, Cartesian coordinates, he's looking at numbers. He wants to know how many meters. That's what he wants to have this. What is it called? A ordered pair, or an ordered triplet, or an ordered quadruplet, and they can keep adding and say quintuplet and so on, and they ended up with infinite dimensions because they can put any number of coordinates there that they want to locate that point if they want to be more and more accurate. What's that got to do with three-dimensional?
Yeah, isn't it more accurate to speak of coordinates than dimensions at that point?
That's what they did.
It's easier to say, look, you have 4. We could use 4 coordinates to find where you are.
No, I'll give you the definition, and you'll understand it perfectly. The definition of dimension is, what is the definition? The number of coordinates needed to locate a point. So they equated dimension with coordinates. They say, what is a dimension? A dimension is the number of coordinates needed to locate a point. So they're saying that location is the same thing as structure. That if we have if dimensions refer to three-dimensionality, which is a structural type of concept, to say that that's equal to coordinates, the number of feet that I need to locate that guy or that point within a box or whatever, that's where we had run into trouble. They equated dimensions with coordinates, and obviously vectors which are something totally different, which has to do with motion. They've equated those as well. So for them, whether it's a dimension, a vector, a coordinate, is the same. And they said, well, if we can do all that, why don't we just introduce time as well and make that a coordinate? And they say, oh, I like that, And then we have the dimension of mass. We have the dimension of craziness. We have so many dimensions out there. You can put anything, temperature, everything's a dimension to them because it's all number lines. They have nothing to do with the physical dimensions, which is length, width, and height.
Yeah, when we're talking about dimensions, what we really mean is how big is something. Not where it is. Or how to find it.
That's another definition of dimension.
Or how hot the object is, or how many atoms.
At a specific time.
Yeah, or how many atoms is it made of?
Right.
Which atom? We don't care about any of that. We
This
care
is the problem.
How big is this item?
And this is the problem. This is the problem with the word dimension of mathematics, and that's how the time ended up being a dimension.
Oh, it gets weirder. You don't even know what dimension. The word dimension in normal parlance means something completely different now. Because of games in Hollywood, it means parallel universe. If you come from another dimension.
Oh yeah, you're in the parallel
that
universe.
That one's new.
Yeah, you can go to the fifth dimension and nobody can find you there, allegedly, right?
That's what.
But I solved this very easily. I say, look, God can hide in the 26th dimension if he wants. I don't care. But there better be a line connecting his chest to mine.
No, but that's what
Straight
they're saying.
line.
That's what they're saying. With a parallel dimension, that parallel universe or another dimension, there is no line connecting you and him.
Why not?
Because it's
yeah, but I mean,
in another dimension.
Yeah, but the guy can say it is so, but he's got to illustrate that for me. He's got okay, show me why I cannot connect. God's in the 26th dimension. Fine, I have no problem with that. Why can I not put a straight line from him to me? That's the only thing I want.
Because we're not in the same dimension.
Yeah, but
I told you
what is that?
I told you.
What does that
already.
mean?
He doesn't want to understand.
No, and if you use four-dimensionality, then it becomes a curve. The straight line becomes a curve.
It gets weird.
Okay, we'll see you tomorrow, same time, same station, and we're going to finish up with time, hopefully tomorrow. Maybe, I don't know if the subject can extend more, but...
if we have time.
Yeah, if we have time. And if time doesn't dilate on us. So don't go too fast. We'll see you tomorrow.